In this section, we're going to be working with vertical and horizontal asymptotes and graphing some rational functions. Now remember, a rational expression is a numerator over a denominator, so we're going to be keeping that in mind. So to get started, let's go ahead and talk about what a vertical asymptote looks like, and then we'll also talk about a horizontal asymptote. So, vertical asymptote. A vertical asymptote is basically where a fraction is undefined. Those are those restriction values that we were finding during the last section. So a vertical asymptote might be this dotted line where the graph never crosses. So the overall graph might look something like this. And I might be getting very, very close to these vertical lines but never crossing. So in this case, let's say I have a vertical asymptote at 4 and another one at -4. So a vertical asymptote is a line that a graph never crosses. Now when we're talking about a vertical asymptote, we're basically talking about where a function is undefined. So for the examples that we're going to be looking at today, remember we have rational expressions as a over b, and b cannot equal 0. A vertical asymptote occurs where b equals 0, meaning where are our restrictions? That we were finding before. So x cannot equal whatever value that we have here. So in our case, x cannot equal -4 or 4. Those are our vertical asymptotes. So for this example, this could have come from an expression, let's say like y equal 2x, and again I'm making these values up. We could have an x squared minus 16. Now if I plug in a 4 and a -4, the denominator equals 0, so that's why these are my vertical asymptotes. So a vertical asymptote you will never touch, never cross. Horizontal asymptote is going to be a little bit different. What happens with a horizontal asymptote is I can cross them locally, but not at extremes. So let's look to see what a horizontal asymptote looks like. We'll show you a couple different examples. So I could have a graph where this is getting closer and closer to the x-axis, but it's never crossing. So this is called my horizontal asymptote. So this is at y equals 0 as my horizontal asymptote, and I'll abbreviate that HA. Over here, my vertical asymptotes I'll call VAs, vertical asymptotes. So this is an example where I get closer and closer to the x-axis, but I never cross. So this is the line y equals 0. Keep in mind, this one also has a vertical asymptote at x equals 0. Because this is the function y equal 1 over x, so this is where my function is undefined at x equals 0. So this is an example of a vertical asymptote where I do not cross the line. The graph that I just drew over here on the left to show my vertical asymptote also has a horizontal asymptote. So let's go ahead and sketch that graph in again real quick. So you can see that this graph is getting closer and closer to the x-axis right here, going toward positive infinity, and over here toward negative infinity. This is my vertical asymptote, horizontal asymptote at y equals 0. Now notice I do cross this locally, meaning near the origin, but I do not cross this at extremes. So a vertical asymptote you never cross. A horizontal asymptote can cross locally, usually near the origin, but not at the extreme. So it can cross locally, but not as we go out toward infinity, in the positive or the negative infinity direction for x. Now we have some rules for finding horizontal asymptotes. Now the rules for finding horizontal asymptotes all have to do with the degree in the numerator and the degree in the denominator. We need to look at the highest powers. So this is the way these look. If I had an expression, let's say 4x to the 5th plus 2x squared plus 1 all over negative 3x cubed plus 7, what I would want to look at are the degree in the numerator and the degree in the denominator. So the highest power in the numerator is a 5, highest power in the denominator is a 3. So that's what I'm talking about in this case, is comparing the degree in the numerator and the degree in the denominator. Well, our first rule is this. If the degree in the numerator is greater than the degree in the denominator, like I have in this particular case, there is no horizontal asymptote. Okay, let's look at another option. Option 2. If the degree in the numerator is less than the degree in the denominator, the horizontal asymptote is the equation y equals 0. In our third case, so this is case 1, let's look at case 2. The degree in the numerator is less than the degree in the denominator, so I could have something like 2x squared plus 4x to the 3rd all over 10x to the 9th plus 7. In this particular case, the degree in the numerator, highest power is 3. It's not just the first power, it's the highest power. Highest power down here is 9. So the degree in the numerator is less than the degree in the denominator. So here my horizontal asymptote for this expression would be y equals 0. Now my third case, I have greater than, I have less than, so now I have to have equal to. The horizontal asymptote is the ratio of the leading coefficients. And I'll show an example of that. So it would be y equal the ratio of the leading coefficients in the numerator over the denominator. So that would be our third case up here. So I could have something like 4x to the 5th plus 9x squared over 2x to the 5th minus 7. Well, in this case, the degree in the numerator is equal to the degree in the denominator, so my horizontal asymptote is the limit, or sorry, is the ratio of the leading coefficients. So in this case, it would be y equal 4 over 2, or y equal 2 would be my horizontal asymptote. So y equal 2. Here, my horizontal asymptote was y equals 0, and here I did not have a horizontal asymptote. So these are my rules for determining my horizontal asymptotes. And you're going to want to have these memorized. Graphing these sometimes isn't very helpful when it comes to finding horizontal asymptotes. Now remember, for vertical asymptotes, basically it's where my function is undefined. So for vertical asymptotes, I look for the denominator. Where does the denominator equal 0? Now when I find my vertical asymptotes, they're always x equal values. Okay, they're not going to be y equals, that's horizontal. X equal are my vertical asymptotes. So let's go ahead and look at some examples of finding asymptotes. Let's go ahead and look at, first of all, the domain for this function. So for the domain of this function, let's call the function h of x equals x plus 6 over x squared minus 36. So remember the domain. I factor first, and then I find my restrictions. The denominator cannot equal 0. So that's x plus 6 times x minus 6 cannot equal 0. Now when I solve for each of these, here I get x cannot equal negative 6. Here I get x cannot equal 6. So the domain is x cannot equal plus or minus 6. Now the next thing I want to talk about is my vertical asymptote. Vertical asymptotes are really easy to find once you find the domain. My vertical asymptotes occur where the function is undefined. So I have a vertical asymptote x cannot equal -6, and I have another one, actually I shouldn't say cannot equal because my vertical asymptote is at x equal -6 and x equals 6. So these are those vertical dotted lines. Now my horizontal asymptote is next. Now for my horizontal asymptote, I just need to look at the degree in the numerator and the degree in the denominator. The degree in the numerator is this implied 1, so the degree in the numerator is equal to 1. The degree in the denominator is equal to 2. Well, the degree in the numerator is less than the degree in the denominator, therefore the horizontal asymptote is y equals 0, because the degree in the numerator is less than the degree in the denominator. So we did all sorts of things here. We found the domain, and once you find the domain, it makes it easier to find the vertical asymptotes. Once we find the vertical asymptotes, then we can go along to find the horizontal asymptotes by just looking and comparing the degree in the numerator and the degree in the denominator. Let's look at another example. For this example, let's go ahead and talk about the domain. And then we'll also find vertical asymptotes and horizontal asymptotes. So for this function, let's call this r of x. Let's look at 16x squared plus x all over x squared plus 5. Okay, so to get started, we know the denominator cannot equal 0. So x squared plus 5 cannot equal 0. Subtracting 5 across, I get x squared cannot equal -5. As soon as I take the square root of both sides, I get x cannot equal plus or minus. The square root of -1 is an I, so I get I root 5. Well, that's a complex number. We're only working in the real number system, so I'd have to say there's no restrictions here. And since there's no restrictions, there's no vertical asymptotes. There's no value that I can plug into that denominator that will make the denominator equal to 0. I can also talk about horizontal asymptotes now. The degree in the numerator here is a 2. The degree in the denominator is equal to 2 as well. And again, I don't look for the first one, I look for the highest one. So here's a 2 and a 2. The degree in the numerator equals the degree in the denominator, therefore the horizontal asymptote is the leading coefficient ratio, so it's 16 over this implied 1, or y equals 16 is my horizontal asymptote. So there's a lot of different things that we can do to these problems, but basically you're just very consistently working through and simplifying these down. Now sometimes when I'm looking at a rational expression, I can simplify it like in our previous section that we were working on. And so when I do that, instead of having a vertical asymptote, what I do is I have a hole in the graph on the values that we can simplify. So let's go ahead and look at an example where that could come into play. So for this expression, let's go ahead and talk about the domain. We'll also talk about horizontal asymptotes, vertical asymptotes, and really holes in the graph as well. Now vertical asymptotes and holes are related, so usually when you're finding one you might come up with the other one as well. So let's go ahead and simplify this expression. Let's call this one b of x. Call it x over the quantity x times x minus 8. So remember, the denominator cannot equal 0. So I have x times the quantity x minus 8 cannot equal 0. So I have x cannot equal 0, and I have x cannot equal 8. Now where I get the 8 from is I take the x minus 8, set it equal to 0, and then add the 8 across. So these are my restrictions. So if I had to talk about the domain, I'd have to say the domain is all real numbers except x cannot equal 0 and x cannot equal 8. Now for my vertical asymptotes, I have the x equals 0 and x equal 8 that I need to think about, but let's look to see what happens. You notice when we simplify, the x over x is 1, and I'm just left with 1 over x minus 8. So, because these cancel, I have a hole in my graph at x equals 0. Now why 0? Because that was my restriction. I have a vertical asymptote at the remaining restriction, x equal 8. So again, I have a hole in my graph at 0 because these were able to cancel, so I had to find my restrictions first. Once I find those restrictions, if any of them cancel, they produce holes in my graph, hollow points. Any restrictions that stay produce vertical asymptotes. Now let's go ahead and look at horizontal asymptotes as well. For horizontal asymptotes, I had x over the quantity x times x minus 8. Well, if we want to compare the degree in the numerator and the degree in the denominator, I'm going to go ahead and distribute through with that x. So the degree in the numerator is 1, it's an implied 1. The degree in the denominator is equal to 2. And if you notice here, the degree in the numerator is less than the degree in the denominator. Therefore, I have a horizontal asymptote at y equals 0. And these are just the shortcut rules that we listed at the beginning of this lecture. So those shortcut rules are going to be very important to know. Now the next thing we're going to be looking at is graphing and transformations. Now when we talked about transformations before, a lot of times what we were looking at was a basic parent graph, and then based on the basic parent graph, we would transform it with a horizontal shift or a vertical shift, and that's what we're going to be doing here. So let's go ahead and look at a couple parent graphs. The parent graphs that we're going to be looking at are rational expressions. So we have one parent graph of y equal 1 over x. The graph of y equal 1 over x is going to equal this nice little graph that we looked at earlier that exists in the first and the third quadrant. Important things to remember: I have a vertical asymptote and I have a horizontal asymptote here. So my vertical asymptote is at x equals 0. This is my vertical asymptote. My horizontal asymptote is y equals 0. So that's one of my parent graphs, y equal 1 over x. Let's go ahead and look at another parent graph as well. Let's look at the parent graph 1 over x squared. These graphs are very similar, except what happens when you square something, remember, it becomes positive. So this part in the first quadrant stays positive. This part that's in the third quadrant pops up top because when I square it, all those numbers become positive. Now I have a vertical asymptote at x equals 0, and I have a horizontal asymptote at y equals 0 as well. So this is the parent graph of y equal 1 over x squared. Now if I had 1 over x cubed, it's going to follow through with 1 over x because both of their exponents are odd. If I had 1 over x to the fourth, it's going to follow similarly with 1 over x squared because both the exponents are even. So those are our basic graphs. Now if I graph these on a calculator, they're going to look a little different perhaps. Sometimes what happens on the calculators is that they connect the dots for the asymptotes. So let's go ahead and look at 1 over x. And we might have to expand our y or x-axis here. We'll kind of wait to see what's happening. Now we don't see much going on right here, so let's go ahead and change our window from negative 50 to positive 50 to negative 10 to positive 10. Now again, our graphs aren't going to be perfect. I can see a little bit more what's going on here with this graph. It gets closer and closer to the axes. And then I can also see under second table, I have a problem here at 0. So this is showing me where things are going wrong here. This is showing me where I have a vertical asymptote. Now let's go ahead and look at y equal 1 over x squared as well. So I have my squared in the denominator. And if you get into a pickle and you're not sure what's going on with some of these graphs, put them into your calculator and let's have a look at them. So I can see here this is in the first and second quadrant. I have a vertical asymptote at x equals 0. So again, keep those in mind while we're graphing. So let's go ahead and look at transformations, and with transformations we can always graph them, and again keep in mind that sometimes when they graph they don't graph really well. They connect some dots that should actually be vertical asymptotes. So let's go ahead and graph the transformation. G of x equals 1 over x minus 6, and let's go ahead and pull out a plus 7 over here. We'll have two transformations. The plus 7 will be a vertical shift up. Seven units. Okay, now it's on the outside of the argument, so that's how I know it's vertical. So this is our vertical shift up. Now what about the minus 6? This is when it's within the argument of the function. So the minus 6 is going to be my other transformation. It's going to do the opposite of what you think, and it's going to be a horizontal. So this is a horizontal shift. Now, this says minus 6, so you think it's to the left. Because it's within the argument, you do the opposite. So a horizontal shift to the right, not left, but to the right 6 units. So I'm going to be taking my graph, my parent graph. My parent graph would be 1 over x. And I'm going to be transforming it. So I'm going to be moving my 1 over x 7 units up and 6 units to the right. So we're going to have to make sure we leave plenty of room here. I'm going to scoot it down a little bit more. Most of everything that's going to be going on will kind of be up here in this area. So my vertical asymptote was at x equals 0, but since I moved it 6 units to the right, 2, 3, 4, 5, 6, I have a new vertical asymptote at x equals 6. And this totally makes sense because my function is undefined at 6. Now my old horizontal asymptote was at y equals 0, but I moved it 7 units up. So my new horizontal asymptote will be right here. So this is at y equals 7. This was x equals 6. And now my graph is the same shape. It's just moved up in this area with the new horizontal and vertical asymptotes. So let's go ahead and graph this as well to kind of compare our graph with what our calculators will show us. So I need to take 1 divided by, this denominator needs to be in parentheses, so I have x minus 6, and then I have that plus 7 for my shift. Yep, shift to the right 6 units and up 7 units. So let's go ahead and hit graph, and again we might have to adjust our window around a little bit here. Okay, so I think I want to move over in this area just a little bit. So let's move further to the right. So let's maybe go up here to 20. And then in my y-axis, I want to go up a little higher too, to 20. Let's have a look. Okay, there it's hitting the vertical asymptote, and we can see it's not crossing in the middle either. So let's go ahead and paste this into our lecture. And then kind of compare those values. And you can see they're remarkably similar. Of course, the calculator graph looks a little bit cleaner. But I could easily sketch in our vertical and horizontal asymptotes. Now your calculator might already have these. written in as a solid line, but you need to understand that they're vertical asymptotes. So this is the vertical asymptote x equals 6. This is a horizontal asymptote y equals 0. So graphing these is helpful. Now when you look at these transformations, again, go off of the parent graph, and then you should be able to talk about all sorts of different things. Symmetry, x-intercepts, y-intercepts, kind of the whole 9 yards. You should be able to find the horizontal asymptotes, the vertical asymptotes, etc. Now this particular graph has no symmetry. And the best way to figure out symmetry is to graph it. And it can have symmetry along the y-axis. It can have symmetry about the origin. That would mean I would put this 45-degree line that bisects the first and third quadrant and be reflective across that. These would be similar to our even and odd function type problems. Now remember, for an x-intercept, y is 0, and for a y-intercept, x is 0. Those are important to keep in mind. Now the last problem that you're going to run into in this homework set is kind of a story problem. I'm going to go ahead and get you started on it to kind of give you a good setup. It's kind of a long problem, but once you get the first part, the other parts kind of fall into place. First part asks us to write a function. So let's go ahead and write a function. It says a company is planning to manufacture mountain bikes. The fixed monthly cost will be $100,000. So even if they don't produce one bike, it's going to cost us $100,000 just to have the building rented, the lights on, and pay our employees. So that's the fixed monthly cost. So fixed is is 100,000. Now it says it will cost $300 to produce each bicycle. So along with the fixed cost will be $300 for each bicycle. If I produce 100 bicycles, then my fixed cost would still be 100,000 plus 300 times the 100 bicycles, and I'd add those together to get my total cost. So this is my cost function. Now the next part, they're going to be asking for an average cost. Now the difference between the cost function and the average cost has to do with dividing by the total number of bicycles, because when you have an average, remember that's what you do, is you divide by the total number of values. So let's go ahead and pull in that next question. And again, that has to do with the average cost. Now once I find the average cost, then I can go ahead and plug in all sorts of different numbers into it. So it says write the average cost function C bar. So C bar of x. Well, the average cost function is just going to be my cost function that we originally started with. So in this case, that would be 100,000 plus 300x. And then I need to make sure that I remember to find the average, you have to divide through by the total number of values, or in this case, bicycles that were produced. So that would be my cost function. Now from here, that's going to ask me to interpret some of these cost function values. Now remember, in my numerator, I have 100,000 plus 300x. That entire value is divided through by x, not just part of it, but the entire value. So let's go ahead and interpret one of the first values that they give us. And then I think you can probably get the rest from here. So we're going to do the first one. So the first one is find and interpret the average cost of 500 bicycles. Okay, so that would mean that we would take our cost function, which is 100,000 plus 300, and in this case they want us to plug in the value of 500 in for x, and then we would also divide through by 500. So if you're very careful about this, you can plug the entire numerator into your calculator and divide it through by 500, and let's see what we get. So in our numerator, we have to make sure we have that in parentheses, so that would be 100,000 plus, and now for our particular example, we had 300x, I believe. Yep, 300x. But our value for x was 500. Close parentheses, because that's my entire numerator, and let's divide that by 500. And we get 500 back. Now, you could also graph the cost function and then just plug in all the different C-bar values that they're going to be giving us. That would work as well. But in this case, I get 500 right back. And I wouldn't expect that for plugging in 1,000. I won't get 1,000 back. You need to make sure that you actually plug in these numbers. So when I plug in 500, for this one, I happen to get 500 back. Again, that's not something you can predict for every single value. Now it asks us next to interpret what C bar of 500 means. So let's go ahead and look at the options that they give us for interpretation. Let me see here. So let's go ahead and interpret these. So this question is saying, how many bicycles are produced a month, it costs blank to produce each bicycle. Well, they gave us 500 here. So this value of 500 was given as the input value. It costs $500 on average to produce each bicycle. This value comes from what I get out when I calculate or plug in those values. This isn't the best example because the input and the output happen to be the same for this case, but just remember the number of bicycles is my input, the output is the cost. Let's go ahead and scroll up here again real quick as well. If we look at the beginning, they tell us what x is. X is the number of bicycles. In this particular case, mountain bikes. So for this section, we're talking about horizontal and vertical asymptotes, and then we're also looking at domains and graphing some transformations. What you want to be careful of here is you're reading the directions very, very carefully. If you have questions about the lecture, please bring them to class, stop by my office, or you're welcome to also go to the Math Center in the library. Good luck.